My name is Cary Lindsey. I'm a research geologist here at the Great Basin Center for Geothermal Energy, which is part of the Nevada Bureau of Mines and Geology, or our Nevada State Geologic Survey here at the University of Nevada, Reno. I've been in geothermal, if you count my years of schooling, for a little over a decade. I'm what I've termed myself as a hydrothermal geostatistician. So I like moving hot water, and I like geostatistics, and I like applying that to finding geothermal systems.
I'm Jim Faulds. I'm the Associate Director of the Nevada Bureau of Mines and Geology and Professor in Geology here at UNR. And I've been working in geothermal for over 20 years now, and I'm a structural geologist, and so focused on understanding kind of the fault controls on geothermal activity and applying that to finding systems that might be hidden beneath the surface.
Well, it's great to have both of you here today. Thanks for the great intro. I'm wondering what sparked your interest in hydrothermal systems and what excites you about it today.
I don't think I had a clue what I was getting into. Um, I had a professor, I was a psychology major, and I had a professor who just told me one day, "You are in the wrong field. This is not what you're supposed to be doing." Um, she encouraged me to look towards the earth sciences, and so I was reading journals and articles online trying to figure out what I wanted to do with my life. And I found an article on geothermal energy, and I think I literally ran into her office and said, this is what I want to do.
And I kind of stumbled into geothermal accidentally. Um, I, um, there was a call for proposals, I believe it was in 2002, and I sort of had ignored it. And a fellow geologist here at the Bureau of Mines and Geology said, hey, you might be interested in this. Can I take you on a little tour of some local areas where there was actually a geothermal power plant? Gosh, it didn't take me but a couple weeks of working on one of the geothermal systems in the area that I kind of caught the bug, and I realized this would be a cool way of applying some of what I had done as sort of more basic research, maybe academic research, and that actually had societal relevance, and got hooked on geothermal energy as being a major source of renewable energy.
I would say it really is that too, to kind of piggyback on what you said. Like,
Mm-hmm.
this is a community like none other I've ever worked in. People would say, "Hey, I want to pick a research topic as a grad student or whatever." But when you come into this space, like I joke that I came for the science, but I stayed for the people.
Mm.
I couldn't agree with you more, Carrie. My next question for us is, how does academia help the geothermal industry progress?
I think you're the perfect one to answer that,
Okay.
for sure.
Yeah, really good question, and on multiple fronts, I think. So, um, in academia, when we're not necessarily worried about the bottom line that industry has to worry about in terms of investments and profits and so on, we have a little bit more leeway to do some basic research or some assessments of geothermal potential that industry just doesn't have the time or perhaps the funding in terms from investors to worry about. And so that can involve regional assessments of geothermal potential and kind of how geothermal systems overall work. But it can also involve detailed analyses of local areas. But what's cool about that is that there's sort of a positive feedback into doing those regional assessments and the detailed analyses of these local areas that is very beneficial to industry, that they can utilize then to reduce, let's say, their risk in geothermal exploration and to make development of geothermal systems more efficient. So, yeah.
I think I'm just really proud to be a part of this specific academic organization because I can see before I got here as an outsider how important the work that we do here at the center and at the bureau affects what happens in the real world with geothermal development. And I've been here as an undergraduate. I was here as a postdoc. I left and was not satisfied and wanted to come back because I feel like the work that we do here is immediately visible out in the industry. I think if you look, and Jim could probably show us some great charts, but if you look at the work that Jim does and the work that other teams here have done, you can see that reflected in the growth of megawatts in the industry. So you can see the impact immediately that we're having. It's almost like we're a subsidy for geothermal, you know? But then you also see it on the academic side. You can see the growth in funding that comes into the university through the work that we do. So it's kind of a win-win for everybody, I think. You know, a lot of the work that we have done over the years has been on conventional hydrothermal systems. And when people think about those, they think about systems that have some sort of surface manifestation. So, you know, whether it's a hot spring or a fumarole or some evidence of a hydrothermal alteration. But what we're discovering in Nevada is probably at least 70% of the systems that we have in Nevada have none of this surface expression. So we call those blind or hidden geothermal systems. And that's been a large part of our focus here at the center is how do we explore for those types of systems. So most of the low-hanging fruit, those with surface manifestations, have been identified already. But the largest power plant in Nevada was a hidden geothermal system, and several other smaller ones were hidden geothermal systems. So how do we find those? And I think our technology and the tools and data that we use have changed over the years from things like the 2-meter temperature surveys, which we still use and we still use for blind geothermal systems, but to geophysics, you know, gravity data, MT data, things like that that really help us get a better understanding of what the subsurface looks like. And I think Jim has really championed a lot of that work. Also, the structural work that you know that we do, and the structural characterization that Jim's worked on for years.
Yeah, and what's interesting is almost 40% of the known geothermal systems in the region are actually blind or hidden. But just about all of those have been discovered by accident up until recently. And by accident meaning a mineral exploration well, and by gosh, they hit hot water, or an agricultural well, and it hits hot water. So that's how most of the known hidden systems were discovered. And so that's a lot when you think about it, 40% of the known systems in the region, and there's about 460 or so known systems. You know, if we could develop then methodologies by which we can target those hidden systems, you know, we really think that kind of the sky's the limit in terms of sort of unleashing the geothermal potential of the region. And you know, I'm not sure we have the answer to knowing which methods necessarily work the best, or whether we can find these hidden systems, whether they're going to have a signal at 2 meters depth, because we can put a 2-meter probe into the ground, and some of these hidden systems actually have enough heat that they show up at that level, 2 meters, about 6 feet below the surface. But we have a suspicion that some of these hidden systems may not show up at those shallow levels. And we need to actually drill a hole maybe down to 150 meters or 500 feet to actually capture or see the evidence for some of these hidden systems. And so that's where the geophysical techniques that Cary mentioned are really important. So that surface geology is really important. The fault patterns are very, there's about 5 or 6 fault patterns that pretty much, as far as we know, control all of the known systems in the region. But there's there's thousands of those kind of patterns in the region. And so which one of those actually then contain a hidden system beneath them? And that's where we need to peer into the subsurface, use the geophysical techniques that Cary mentioned. And that gives us a window into the subsurface and allow us to more carefully target where we might drill, and also which one of them more likely actually contains a hidden system. And again, it's all about reducing the risk in exploration and making it more economical. So,
My next question for you is, how important is this data, and how are these modern tools improving our efficiency at finding hidden systems?
yeah, so I think AI tools and machine learning there's a lot of potential there for utilizing those techniques to sort of train on the sites that we know that are positive, where we know there are good geothermal systems, and use those as analogs to find these hidden systems. One problem with that, though, is that we're not necessarily, even though we have maybe better data in this region than we do on most places around the globe, we're still data poor. Most of Nevada lacks that kind of data that we need to identify these hidden systems. And until we enhance those data sets, it's going to be tough for, I think, machine learning techniques, AI techniques, to be as successful as they could be. A really important aspect to accelerating geothermal development will be acquisition of these data sets across much of the region.
And it sounds greedy on our part because we really are lucky in Nevada. We have more data than just about anybody else, but we still feel like we don't have enough. One area that I've used machine learning and that I see it in having a lot of benefit is kind of ranking how we explore, right? Like using unsupervised machine learning to tell us which of these systems looks the most similar to our training data, which we don't use training data in unsupervised, but similar to that, right? What looks the most like the systems that are producing. The problem with that is we're training on one type of system, right? There could be 3 or 4 different types of systems that we should be training on. But I think when I first started doing machine learning and applying it, I was so excited about it. And we're going to get rid of all the expert driven, we're just going to go, all that's going to go away. But I think I've come to learn there's nothing that can replace the people who do this research and the knowledge that they have. So I think we need some sort of combination of these data-driven machine learning techniques, but also just the knowledge that these geologists and engineers have about the systems too.
And then in terms of thinking about some of the regional data sets that are important to have, that maybe we could utilize these AI techniques for. Let's take geological mapping, for example, and that's basically a map of the surface of the Earth that shows all of the different rock units, the different types of rocks, and where the faults are cutting through those rocks. Only about 25% of Nevada, for example, is well mapped such that we don't have to do any additional mapping to explore for geothermal resources. And then if we take our geophysical surveys, one important type of geophysical data set is gravity. Subtle differences in gravity can tell you about where faults are located in the subsurface, particularly in our basins across Nevada. And people think of Nevada as a mountainous state. It is. It's actually kind of the most mountainous state in the country, at least in terms of the greatest number of named mountain ranges. But half of Nevada are these basins, and we probably know more about the surface of the moon than we do what's underneath our basins and where those faults are, and that's where most of our geothermal systems are. So in terms of, let's say, detailed gravity data across Nevada that can tell us where these faults are in the subsurface, gosh, maybe about 10% of Nevada, 15% at the most is covered in that kind of detail. So so we've got a lot to learn still, okay, about our subsurface geology and where these hidden systems might lie.
Yeah. It seems pretty obvious to me how we can take the geophysical data and increase our ability to map the subsurface. The challenging part for me is understanding how our geology and our geophysics can integrate into the exploration process.
I mean, I think the biggest, if we're going to say what tool do we use to integrate all this, we've been doing play fairway analyses here at UNR for a decade now. And I think that's a really cool tool that came over from oil and gas, which actually integrates your geologic data and your geophysical data, even civil data, if you want to go that far as to incorporate that into these models with different weights and different layers so that you can kind of reduce your risk and identify areas that are more favorable than others. And I will say this space is probably one of the most multidisciplinary spaces, right? And just the team that we have right now as part of the Ingenious project, we've got geologists and geophysicists and engineers, and everybody has their own thing that they do, right? That it's just not possible to do it without each other, right? We've got our geophysics folks who go out and collect the data, but collecting the data is one thing, modeling it is another, interpreting it is another, defining how you're going to include that in a resource model is another, and a different type of person has to make each one of those decisions. So I think it's really cool. That's part of the reason why I chose geostatistics, is because I actually get to work with each one of those disciplines. I don't have to pick one. I can work with all of them.
Play fairway analysis is so important because you're combining all of these different data sets into kind of a cohesive model, and you're utilizing let's say, some of the known systems as kind of training sites or benchmarks to understand which of those many data sets are important, or most important. So we know that, God, we should be thinking about maybe 15 or so different data sets, but some of them are more important than others. And the beauty of play fairway analysis and the geostatistical analyses that people like Cary do is that they can basically analyze that problem and say, okay, this particular data set should be weighted maybe 3 times as much as this other data set. That other data set is still important, but not as important as some of the others. So, and those weightings are really important and ultimately give you a very quantitative sort of result in terms of where, what's more likely what area is more likely to contain that hidden system out there. So.
Our next question is, how important is it to study crustal and lithospheric scale processes? And do these deeper processes hold the key to identifying hidden systems?
Yeah, they're very important. It may be more important than one might first recognize. So one of the data sets, for example, that we've been applying to understanding geothermal potential is something called the strain rate. And that basically has to do with tectonic deformation of a particular area and at what rate is that occurring. So for example, Nevada is being pulled apart, it's being stretched, and that's happening before our eyes. It makes Nevada the 3rd most seismically active state. So that crustal stretching is really important because the faults, when you're stretching the crust, have just a little bit of dilation on them. And if you're spreading those faults apart, then fluids can more readily flow through them. Furthermore, you're stretching the crust, you're thinning it, and bringing hotter material, let's say from the mantle, up closer to the surface. So you have what's called a high geothermal gradient, and that's just a fancy word for the rate at which temperature increases with depth. And the other part is a little bit more philosophical, and that is if we develop these renewable resources, then we can produce energy for many, many decades. And some of our geothermal power plants in Nevada have been operating for 40 years now, and many more for 30 years. They're still producing energy. We don't necessarily know how long these systems can operate. Naturally, with time, the temperature can cool down slightly. If you develop a system, it can cool down slightly, and you can lose what we call some of the pressure, some of the fluid flow, as you're using the hot water to generate, let's say, power. But nonetheless, some systems are still pretty healthy after 30 or 40 years. And maybe they can run for another 30 or 40 years, or maybe another 100 years. We don't really know yet. The Earth is pretty happy keeping that spot flowing for long periods of time. It might be thousands, tens of thousands, or hundreds of thousands of years. I'll just say thanks to Cary. We had our first geothermal open house earlier this year, and hope to continue that.
This next year, it'll be the week before Earth Day here on campus at UNR, so we'll call it our geothermal town hall, and it's really just to get the community in to ask questions, express concerns, learn whatever you want to learn about geothermal. We had a great panel of experts last year. We'll do that again. And then if you just want to follow us and see what we're doing at the center, you can find our website. It's GBCGE, so just the initials for the Great Basin Center for Geothermal Energy, gbcge.org. And, all of our faculty are on there. We list students on there and programs that we've got going on. And just feel free to shoot us an email or reach out. We're always glad to talk things geothermal.